Hey everyone, welcome back to The Explainer. Today, we're completely tearing down the 2026 procurement guide for the best metals for plasma cutting. So if you're out there managing RFQs, making purchasing decisions, or maybe you just really want to deeply understand how to optimize your fabrication sourcing this year, you are absolutely in the right place. We're going to bridge that gap between heavy industrial engineering and smart, efficient procurement strategy.
So, let's start with a hard truth, all right? Choosing the wrong metal for your plasma cutting project isn't just some minor technical hiccup. It directly leads to massive hidden costs, really expensive secondary labor, and agonizing supply chain delays. It's all about optimizing your total cost of ownership, not just looking at what a plasma torch can theoretically manage to melt. When you mismatch your material to the actual cutting technology, well, your budget is going to pay the price.
Okay, let's dive right into this. We've got a highly structured 6-step roadmap for today's technical breakdown. We're going to quickly cover the sourcing landscape, the metal variables that matter, a head-to-head Big Three showdown, the crucial trade-off of speed versus edge quality, smart RFQ partner evaluation, and then we'll wrap the whole thing up with 2026 sustainability trends. Number 1, the sourcing landscape, and really, the core requirement. So what's actually going on out there on the fabrication floor? Well, plasma cutting essentially operates by creating an electrical channel of superheated, ionized gas. That's the plasma itself. And that is used to melt and aggressively blow away the metal. And this brilliantly illustrates our first major sourcing constraint. Because this is strictly a metallurgical process, electrical conductivity is the non-negotiable first step. Unlike laser cutting, which can comfortably slice through non-conductive materials like plastics or wood, plasma absolutely needs a conductive metal to close the circuit and actually function. Moving on to number 2, metal variables that matter. These are your performance factors.
Now, what's really interesting here is how physics translates directly into dollars and cents. You have thermal conductivity, which measures how fast heat moves through the metal. Then there's the melting point, and that determines the sheer electrical amperage needed from the plasma machine itself. And finally, oxidation levels, which absolutely dictate the cleanliness of your cut edge. These 3 factors working together directly determine if a part comes off the cutting table clean and ready to go, or if it's going to require expensive, time-consuming secondary machining before you can even use it.
But hey, before we get into the specific metals, I want you to keep this exact range in mind. 0.25 to 2. That's 1/4 of an inch to 2 inches. This is the absolute thickness sweet spot for plasma cutting. If you're sourcing materials thinner than 1/4 inch, honestly, a fiber laser is often way more cost-effective, just because of its sheer speed. Over 2 inches, you're usually looking at oxy-fuel or water jet technologies for your carbon steels.
All right, section 3. This is the fun part, the Big Three showdown: mild steel, stainless, and aluminum.
Let's kick it off with mild steel, or carbon steel. This is the predictable gold standard for plasma tables everywhere. It is simply the most cost-effective and reliable material you can choose. In fact, in 2026, if your supplier uses high-definition plasma systems, you can achieve near laser-quality edges on mild steel up to 2 inches thick. It's incredible. The only real caveat here is that you have to make sure the surface of your steel is free of heavy mill scale and rust, because those impurities will deflect the electrical arc and rapidly increase the wear and tear on the machine's nozzle.
Next up, we have stainless steel. You can kind of think of this as the specialized diva of the fab shop. Unlike mild steel, which actually oxidizes or burns to practically assist the cutting process, stainless relies entirely on the pure, raw heat of the plasma. Because it lacks that chemical assist, cutting stainless is generally 15 to 25% more expensive than mild steel. It demands much slower travel speeds and requires specialized secondary gases, things like nitrogen or an argon-hydrogen mix known as H35, just to prevent ruining the material.
And rounding out the Big Three is aluminum, the highly reflective, lightweight challenger. As global industries push relentlessly for lightweighting in their products, aluminum sourcing has just surged. But it has extreme thermal conductivity, meaning it pulls heat away from the cut zone very rapidly. Now, older plasma units really struggled to maintain a melt on aluminum, but modern 2026 systems actually handle it beautifully by utilizing water injection or dual gas setups to control all that massive thermal bleed.
Which brings us to section 4. Speed versus edge quality, the ultimate trade-off.
Now, what's really fascinating here is the direct contrast between processing speed and the final edge finish quality across our 3 metals. Let's break this down. Take mild steel. You're looking at a high processing speed and a flawless 5 out of 5 for edge quality. It is the perfect marriage of efficiency and finish. But then contrast that with stainless steel. Because of the sheer thermal demands and the pure heat required, the processing speed actually drops down to medium, and the edge quality dips slightly to a 4 out of 5. And finally, look at aluminum. Aluminum ramps the processing speed right back up to high, but you take a pretty noticeable hit on the edge finish, coming in at just a 3 out of 5. As a procurement professional, you're constantly managing this exact trade-off depending on what metal you choose. How fast can the supplier cut it versus how clean that edge will actually be when it finally arrives at your dock.
And when that edge quality rating drops, it manifests as physical defects on your parts. For stainless steel, the primary edge risk is called sugaring. This is a severe, really ugly oxidation on the edges that happens if the fabricator uses the wrong gas mix. For aluminum, the dominant risk is dross, which is a hardened, stubborn slag buildup right on the bottom edge of the cut. I really want to warn you about this. Both sugaring and dross mean extra manual labor. That translates directly to higher labor costs secretly baked into your RFQ to grind, sand, and clean those edges down to spec.
Section 5. Smart RFQ Partner Evaluation, or simply put, vetting the supplier.
Our source material hits the nail right on the head here. It says, the best metal is only half the equation. You must evaluate the supplier's capability to handle specific plasma materials. Selecting the absolute perfect alloy on paper is completely useless if your chosen fabrication partner lacks the specialized equipment and the knowledge to actually execute the cut.
So it all comes down to knowing exactly what to ask them. First, demand to know, do they use high definition or HD plasma? HD systems offer significantly tighter tolerances, down to 10 or 20 thousandths of an inch, which might completely eliminate your need for secondary machining altogether. Second, what's their gas delivery system? If they're just hooking up cheap shop air to cut your expensive stainless steel, the edge quality is going to be abysmal. Specialized metals require specialized gas delivery, period. And finally, what are their minimum order quantities, or MOQs, for specialized alloys? Most shops stock standard mild steel, sure, but they might force you to pay for a massive full sheet of high-grade aluminum, even if you literally only need a small bracket cut.
And finally, Section 6, 2026 Sustainability Trends, the Green Mandate. Look, sustainability isn't just some corporate buzzword anymore. It's a hard procurement metric. First, you need to ask about their nesting software efficiency. Nesting is the algorithmic process of arranging your parts on the raw metal sheet. Better nesting means significantly less material waste, and that efficiency should be passed directly on to you as a lower per-part price. Furthermore, major brands are heavily pushing for recycled content documentation. Make absolutely sure your supplier can provide mill test reports, or MTRs. These documents trace the exact chemical and physical properties of the metal, and they are vital for proving compliance in the 2026 manufacturing landscape, particularly for high-volume steel and aluminum.
Which brings us to our final takeaway for this explainer. I want to leave you with a provocative question to ask yourself the very next time you review a quote. Is your fabrication partner optimizing for their speed or your total cost? It's a vital distinction. True optimization requires balancing those material properties, machine wear, and that sneaky secondary labor. Keep asking the right questions, demand the right setup for the right metal, and I'll see you in the next explainer.